Welcome to another unit in this workbook, Statistics. This time I'm going to talk about confidence intervals. In particular, I'm going to talk first about the confidence intervals for the mean and then for the variance. But first, what is the general idea behind a confidence interval? Well, if we want to calculate the average or the mean of a sample, we can simply use the formula for the arithmetic mean. The problem, however, is the arithmetic mean is just an estimate, an approximation of the real mean. There's always errors involved in this. So if I actually want to know something about the real mean in the sample, I might get the idea to use a confidence interval around the arithmetic mean to know that the real mean will be with a percentage probability of X% somewhere in the area demarked by the confidence interval. For example, in this case, I have here 60%. I could say, well, with 60% certainty, the real mean will be somewhere in this area around the arithmetic mean. The interesting thing with this is, the more observations I have, the better my arithmetic mean become, and the smaller the confidence interval gets. So if I just have enough observations, I will have very small confidence intervals, so I could be really sure about the results I'm getting there. Well, so much for the general idea. Let's take a look at confidence intervals for the mean. And, well, here we're going to take a look at two versions. The first version where we already know the variance or the standard deviation and where we can use the normal distribution to actually determine the confidence interval. And the next one would be the one where we do not have any such information and we have to use the t-distribution. So the first version, we have a normally distributed population. We do know something about the variance or the standard deviation. In this case, we can use the normal z-distribution, which is nothing else than the normal distribution. In this case, the two-sided confidence interval looks like this. Two-sided means we have a value to the left and a value to the right. So we determine somewhere in this area the real mean lie. It's more or less equally wide in both directions from the value we used as an approximation, the value being the arithmetic mean. Well, how do we go about this? We take the arithmetic mean, then either we subtract or add standard deviation divided by number of observations, the square root of this, and this value from the distribution. Well, we see two things here. First off, by dividing with the square root of the number of observations, the more observations we have, the smaller the deviations from the arithmetic means become in both directions. So the more observations we have, the smaller the interval will actually be. Also, if our data set is fluctuating much more strongly, then we will have larger standard deviations and the intervals will automatically be larger. So if we have relatively stable data sets, not a lot of fluctuations there, values all close together, we will automatically get smaller confidence intervals. Well, as I said, we have two-sided intervals and we have one-sided intervals. One-sided intervals where, in this case, for example, we assume that the mean would be larger than this. So if it should be larger, well, it could fluctuate a little bit to the left, but only a little bit. Because to the upper side, well, we don't care. If it should be larger, well, could be whatever, at least it's larger. But fluctuations to the left might be critical. The other way around, in this case, fluctuations to the right might be of a problem. That's why we only need to consider this side. But however, this always depends on what's the objective we're talking about. Oftentimes what I've seen is that you use two-sided intervals. In either case, for testing, one-sided tests might actually make a lot of sense, but for intervals, it's usually two-sided ones which are used. Well, that's a version, as I said, with the known variance. Let's now, after we talked about this, discuss the versions where we do not know our variance. That's the t-distribution version. Again, we assume normally distributed population. We do not know the variance, so we use the t-distribution and calculate the sample standard deviation from our data. That's why here, instead of the standard deviation from the previous slide, we use our sample standard deviation, and instead of the z value, we're using the t value. We're using the t-distribution. Generally speaking, the idea, however, did not change. Still the same general idea. The only difference, we estimate as well the sample standard deviation, and we use the t-distribution. That's also something which leads to the point that intervals determined in this way, with the t-distribution, with the sample standard deviations, usually are larger than the ones where we already know the variance and where we can use the z-distribution, because those values usually are larger than the values from the z-distribution, and those values are larger than the given set standard deviation. Well, that was everything on confidence intervals for the mean. However, we can do the same thing for the variance as well. We can do the same thing for the variance as well. Here, for the variance, we as well assume normally distributed population. Well, we do not have any assumptions for the variance because, well, if we want to have a confidence interval, it's not given. And in this case, we're going to use the chi-squared distribution. Why the chi-squared distribution? Because it's a squared value here. Whenever we have something to do with squared values, which are normally distributed, we use the chi-squared distribution. And the interval looks like this. So it's our estimates for the variance, left and right, multiplied with the number of observations, divided by the respective value from the chi-squared distribution. That's actually an important aspect. Here we have 1 minus 1/2 alpha, and here we have alpha half. And that's something which often is overlooked, and why in the tables for the chi-squared distribution we also have values like 0.01, 0.05. That's where we need them for, this part here. And well, that's then everything for this unit. Hope you enjoyed this unit on the confidence intervals. I say goodbye and see you next time.